Hello. In this session, we are going to continue with our lessons on leaching, which is solid liquid extraction. In this lesson, we are going to look at multi-stage countercurrent leaching. Let's look at our lesson plan. We are going to start with the introduction to multi-stage countercurrent leaching, and then secondly, we will look at mass balance for multi-stage countercurrent leaching. Then we will start looking at the two cases of multi-stage countercurrent leaching, which are variable underflow and constant underflow. In multi-stage leaching, the underflow from the first stage is fed to the second stage to extract more solute in order to improve recovery. Also, the solution feed to a given stage comes from the next stage in a sequence in order to load it with more solute. As you can see, the underflow from stage 1, which is this underflow, it gets fed into stage 2 in order to continue recovering more solute from the solids. And also, the solvent feed to stage 1 comes from the stage 2, which we are now in stage 1, continuing to load it with more solute. The operating principle of countercurrent multi-stage operation is to maximize extraction potential across the stages by contacting the exhausted underflow with fresh solvent, and at the same time contacting the loaded solvent with fresh solids. This is the same operating principle that is used in optimizing the driving temperature difference in countercurrent heat exchangers. If you could remember, in countercurrent heat exchangers, we are always trying to maximize the delta T between the two streams. A flow diagram of a countercurrent multi-stage leaching process is shown here in this figure, just to sort of like familiarize you with the system, how it works. And furthermore, we are showing another diagram which we have taken from our references in order to illustrate the stage layout and numbering using Morsets and breaks. This will be your stage 1, your stage 2, and then if you break you to stage N somewhere in the middle, the feed to stage N will be Ln minus 1, the underflow feed, and then the overflow coming from that stage will be Vn, and then the solvent feed to that stage N will be Vn plus 1, and then the underflow product from that will be Ln. Just basically familiarizing you with the notation and numbering of the continuous multi-stage countercurrent leaching process. The final stage is also shown here, just showing that if you have n stages, the solvent feed, it will be numbered n plus 1. So if you have 50 stages, the solvent feed will be numbered V51. The stages are numbered in the direction of the flow of the solids, that is in the direction of the underflow stream. So the stages are numbered from left to right. To make the referencing simpler, let us familiarize ourselves with some terminology. Let us refer to the following phases by these naming conventions. The liquid overflow phase that flows continuously from stage to stage from the direction of fresh solvent towards the direction of loaded overflow, which is the direction, the loaded overflow, which is the leachate or the extract, will be referred to as the overflow phase, which contains the solvent plus the solute phase. It will also be referred to as the V phase. The composition of solute in the V phase will be denoted by X. The solution occluded or entrained in the underflow slurry that flows continuously from stage to stage from the direction of the fresh solids towards the direction of the loaded or depleted solids or the raffinate will be referred to as the underflow phase or the L phase. Note that this is also a liquid solution phase with solvent C and solute A. The composition of solute in the L phase will be denoted using Y. The solids in the slurry underflow phase, when referred to separately without the inclusion of the solute, will be referred to as the B phase or the solid phase. It is assumed that the solid B phase is insoluble and is not lost into the liquid V phase or the liquid L phase. The slurry phase will be reserved for referring to the combined underflow slurry, which includes the solids and its entrained solution L phase. Before we continue with the mass balance, let's just review the naming conventions of the phases that we have just been discussing in the previous slide. We have stated that the solvent liquid phase, which is the solution, and the solvent, which is the solution which contains the solvent and the solute, the overflow, will be referred to as the V phase or the overflow phase. In the underflow, we have the solids and the solution. The solution in the underflow will be referred to as the L phase, which contains the solute and the solvent. The solids by themselves in the underflow without the inclusion of the solutes or the solvent will be referred to as the B phase. Okay, we can then derive the overall mass balance and component balance of the solute A over n stages as follows. The first thing that we will do is we will draw the system boundary, and then we will do our mass balance around that system boundary. If we look at the system boundary, we have the overflow coming out, this solid feed coming in, the solvent coming in, and the underflow coming out. So the overall mass balance will be all the incoming streams, Vn plus 1, which is the stream here, and the incoming slurry stream, Lo, which is the stream here, plus V1, which is now the outgoing streams, this stream here, and then Ln, which is the stream here. Please note this overall mass balance is done on the solution. It does not look at the solids, as you can see that we are only looking at the V and the L phase. Furthermore, we can do the component balance on the solution overall mass balance by looking at now at the solute. What we will do is we will multiply the solution flow by the mass fraction of the solute in the solution. For the solvent feed, we know that it will be the solvent flow multiplied by the concentration of the solute in the solvent. For the slurry feed, it will be the solution in the slurry feed multiplied by the concentration of the solute in the slurry feed. For the overflow, which is now the product stream, will be the flow rate or the mass flow of the overflow multiplied by the mass fraction or the concentration of the solute in the overflow stream. The underflow stream, which is the raffinate, will be the flow of the solution in the underflow multiplied by the concentration of the solute in the underflow solution. Please keep note of the fact that the V phase, the composition of the solute is denoted by X, and then in the L phase, the composition of the solute is denoted by Y. And also, please note that how we do our mass balance, we are looking at the incoming streams, which are these streams, and equating them to the outgoing streams, which are these streams. So in case you have missed it or I did not go very clear on it, we do our mass balance by equating the output to the input. Similarly, for the component balance, we will be equating the input to the output. We can now rearrange equation 5, which is the equation of the overall mass balance across the system boundary, in order to express the solvent feed in terms of the other three streams. So the solvent feed stream will be expressed in terms of the underflow, the overflow, and the solution in the slurry feed. Once again, let me reiterate, this balance is done on the solution. We are not yet considering the solids. We are only looking at the solvent and the solute. We are looking at A and C. And then now we can rearrange equation 6 to make the composition of the solute in the solvent feed stream, which is xn plus 1, the subject of the equation as follows. Remember, this is equation 6. We have now taken the balance of the component in the slurry feed to the right hand side, and then we only have the solvent feed on the left hand side. Then we can divide by the total solvent flow in the feed to find this equation, which now has the composition or the mass fraction of the solute in the solvent feed as the subject of the equation. Furthermore, we can now substitute the total solvent solution feed, Vn plus 1, as we have expressed in equation 5, into this equation. Now that we have this equation only now in terms of the underflow streams and the product output streams. So now what we have is we have the equation that expresses the composition of the solute in the solvent feed as a function of the composition of the solute in the liquid underflow Ln phase. This equation here, equation 7, is the equation of a multi-stage countercurrent circuit operating line. When this equation is plotted on the xy plane, it passes through the mass balance points or nodes of the circuits, which are the terminal points that make point x1, y0, and then point xn plus 1 and yn. It passes through these two nodes here. The node that makes a point x1 and y0, and then the point that makes node xn plus 1 and yn. In the real leaching application process, as the solution becomes concentrated with solute A, its viscosity and density are likely to change considerably as you move from this point to that point. If this case occurs, then the solids in the lower numbered stages, where it is entrained with a high solute concentration, the solids here in the lower numbered streams, like from 1 upwards, where these solids are entrained with the solution that has higher concentration of solute, are likely to retain more solution than the solids in the stages with dilute solute concentration, which is the solids on the high numbered streams or the high numbered stages. So what we are saying is the solids here are likely to retain more solution than the solids on this side. In this situation, the underflow solution Ln retained in the solids underflow, that is the solution in the L phase, will vary significantly and will result in variation of the slope of this equation here. As you can see, this equation, the slope of this equation is dependent on the entrained liquid, in particular Ln. In this situation, we have an operation called variable underflow. As you can see now, the solution in the underflow changes from being very high in the lower numbered stages to being a little bit less in the higher numbered stages. Please note that the overflow will also vary, as the overall mass balance has to be conserved and balanced. So the overflow the V phase will also change because the total solution balance has to be conserved. If the amount of solution in the L phase does not change as we move across from lower number stages to higher number stages, and the solution retained in the underflow from stage to stage does not change with the solute concentration, we will end up with a situation that is referred to as the constant underflow, where now the underflow L phase, the total flow of the L phase, does not change and remains constant from stage to stage. This will result in a simplified stage-by-stage calculation, which is the constant underflow phase. We are now going to look at the variable underflow, and then after we have looked at the variable underflow, we will look at the constant underflow. The variable underflow leaching operation is very similar to the liquid-liquid extraction, where the flow rate of L and V changes from stage to stage, which means that as you move from this stage to this stage, the values of V and L will change. That's essentially what that means. The overall total solution balance, that is the balance of solute A and solvent C, can be done around the mass balance boundary as we have drawn it here, as follows. The input will be equal the output, which we will equate it to some mixture M. So the input streams, which is this stream plus this stream, will be equal to this stream and this stream, which are the output stream, and we will equate that to some mixture M, where M is the total mixture of flow rate in kilogram per hour of solute A and solvent C, which are contained in the input or the output. We can also do component A balance by using the mass fraction of solute A and multiply them by the total solution flow rates as obtained in equation 8 above. We end up with equation 9 here. So what we do is the solution in the slurry feed multiplied by its composition YO plus the solution in the solvent feed multiplied by its composition xn plus 1 will be equals to the solution in the underflow product Ln multiplied by its composition plus the solution in the overflow product stream multiplied by its concentration x1 will be equal to some total mixture M multiplied by each solute concentration xm. Furthermore, we can do the total overall solid balance. Now we will look at the solid balance around the system boundary, and we know that the solid flow is only in the underflow, so we'll only be looking in the input and the output of the underflow. And we know that the solids from the previous lesson, lesson 1, which assuming that you would have watched before you watched this lesson, we know that the total solids flow will be denoted by B, which does not change across the underflow, which can be found by multiplying N, which is the ratio of the solids divided by the solution in the underflow. That will give you the, if you multiply it by the solution flow, will give you the total solids flow. And then we know that the solids flow does not change across, so you can do this balance for all stages. So since we are only looking at the system boundary, where we're only looking at the inlets and outlets, we only do it for the inlets and the inlet and the outlet, and we know that it will be the solids, the total solid in the mixture, total mixture M. Let us review this again just to recapture what we have just said here when looking at the mass balance of the variable underflow countercurrent leaching operation. So what we are saying is, if you look at the total overall mass balance across the system boundary, you will have the two inlet streams combining or mixing to form the total mixture M, and then the mixture M separating to form the two product stream V1 and Ln. Remember, this is now becoming a bit more similar to liquid-liquid extraction. We are saying that the inlet streams will mix to form M, and M will separate into the two outlet streams Ln and V1. What we have done differently or in addition here is we have now included the total overall solid balance, which we haven't been doing in the previous mass balance that we have just concluded in the previous slides. As before in lesson 1, xm and nm are coordinates of point M, which is the mixture point, on the n versus xy plot, which is also known as the operating diagram for the process. The coordinates nm and xm can be calculated from equations 8, 9, and 10, and the position of M can be located on the operating diagram as shown here. As shown before for a single stage calculation in lesson 1, point LO, M, and Vn plus 1 must lie on a straight line because point M is made by mixing Vn plus 1 and LO. And then also point Ln, M, and V1 must lie on a straight line because Ln and V1 are made from the separation of mixture M. Usually, from the design specification and requirements, the flows and composition of LO and Vn plus 1 are known, and the desired exit concentration of the raffinate Ln, which is Yn, is usually also set. Point LO can be positioned by using YO and NO, which can be calculated from the given slurry conditions. Point Vn plus 1 can be positioned using the coordinates Yn and Nn, which can be calculated from the flow and composition of the solvent feed, which is also usually specified in the problem. The straight line LOM Vn plus 1, which is the straight line, the red straight line, can be drawn on the operating diagram connecting points LOM and Vn plus 1 as shown in the figure, as I've just demonstrated. Point Ln, which is the raffinate underflow, can be positioned using Yn and Nn, and then we can now draw a line moving from Ln to M, passing through M, and then we can position point V1 by further extending this line to find the point V1, which is on the x-axis intercept, which is on the n is equals to 0. Remember, the V is always on the n is equals to 0 line, which is the x-axis. In order to do a variable underflow calculation, we first need to derive the equation for the operating point delta. We start by doing total mass balance on stage 1 and on stage n as shown in these figures here. Looking at stage 1, we will do the balance over the input, equating them to the output. The input for stage 1 will be LO, which is this one here, and V2, which is the stream here, which will be equal to the two outgoing streams, the output, which is L1, which is the stream here, and then V1, which is the overflow product stream. Similarly, for stage n, we will do the input and equate that to the output, where we know the input will be the n-1 stream plus the vn+1 stream. Then the output will be the underflow ln plus the overflow vn. Remember, again, the balance is done on the solution, which will be the solute plus the solvent, A plus C. We can rearrange the two equations to express the difference between two passing streams from stage to stage. We end up with equation 2. What we are doing actually here is we are expressing the difference between the two passing streams. We look at two passing streams in each case. The two passing streams will be this stream here. Let me just change the color. The two passing streams will be this stream here and this stream here. The difference between these two streams should be the difference between this stream here and this stream here. And then also the difference between the two passing streams, this stream here and this stream here, will be equal to the difference between any two passing streams. So let's look at this. The difference here would be equal to the difference here. Okay, let's look at that again. When looking at stage 1, the difference between two passing streams will be the Fitzgerald solution, which is LO, minus the overflow V1 will be equals to underflow L1 minus the feed solvent stream, which is the overflow feed V2. The difference is equals to delta in all cases. You can do that for this stage n as well. The value is constant and holds for all n stages. So if you had all the other stages here in between here, the difference between all the passing streams will be equals to delta. We can now use that to express the difference for all stages as follows. The delta will be equals to stream LO minus V1, L1 minus V2, and then it will carry on for even stage n, and then the final stage capital N. We can further use this solution balance equation now to calculate the component A balance to find the delta, X delta, which is the mass fraction delta of component A in the two passing streams. As you know, what we will now be using is the equation of the component balance of A for each two passing streams. So we will use equation 13, but instead of using the solution balance, we will now do the solute A balance as shown in this equation here. Then by rearranging this equation, we can find the X delta, which is given by this equation 16, which is just by rearranging the equation 15. If you look at it, it will just be saying A delta is equals to the difference in the amount of A, fraction of A, divided by the difference of the total solution balance. Okay. Furthermore, equation 17 may be used as a derivation of equation 16 to do the X delta for all stages, starting from stage 1 to stage capital N. Then we can continue with the solid balance to find N delta, which here you see we have used stage 1, and then also stage 1 on the inlet and stage 1 on the outlet, the two passing streams. Okay, remember now, if we have X delta and N delta, we have the coordinates for positioning point delta on the operating diagram, which is the diagram of N versus YX. The location of the operating point delta on the N versus XY diagram, which is the operating diagram, can be located at the coordinates X delta and N delta, which we have calculated in the previous slide as shown here. This point can be located graphically as the intersection of the extensions of line LOV1, which is this line here, the extension of that line, and that of line LN Vn plus 1, the extension of that line, where they intersect, will be the location of our operating point delta. This intersection can be explained using the mixing rule and rearranging the delta point equation that V1 is equals to LO plus delta. Remember, the original equation was V1 minus LO is equals to delta. So we just rearrange it in such a way that now we give V1 is equals to LO plus delta. Therefore, if you look at it this way, V1 must lie between points LO and delta, because if we mix LO and delta, the resulting mixture will lie in between the 2 points. Similarly, Vn plus 1 is equals to Ln plus delta if you rearrange the equation, which was originally Vn plus 1 minus Ln is equals to delta. Therefore, Vn plus 1 must lie between the points Ln and delta, because if we mix Ln plus delta, you get a point in between lying on the line that's connecting those 2 points. And since delta is the same point for any 2 passing streams, the 2 lines must always, all the lines must always intersect at delta. All the passing streams must always intersect at delta. The line connecting the passing streams must always pass through a point delta, which means that if you look at V2 and L2, the delta between V2 and L2, you will find that V2 will lie on the point connecting L1 and delta. Similarly, V3 will lie on a straight line connecting the 2 points that are connecting L2 and delta. This will carry on for Vn plus 1 will lie on a line that's connecting Ln and delta. You will see this as we start to build on stage-by-stage calculations in the next few slides. The general point to take forward here will be that all the lines connecting the 2 passing streams will have a common intersection at the operating point delta. Furthermore, let us state the following to make the next step easier to understand. The positions of V1, V2, Vn minus 1, and Vn will be located on the n versus x line, which is on the x-axis. Remember, the n versus x line is on the x-axis where n is equals to 0. Then the positions of L1, L2, Ln minus 1, Ln will be located on the n versus y curve, which is this equilibrium line here of n versus y. Remember furthermore that Vn and Ln are the 2 streams leaving stage n, and therefore they are in equilibrium. The 2 streams that are in equilibrium are connected by a tie line. So for an equilibrium type of y equals to x, as we have stated in the first lesson, that the tie line for this equilibrium are vertical, indicating that yn is equals to xn. So the compositions of the solution that is entrained in the underflow leaving stream n is equals to the composition of the overflow of stream n. So Vn, the composition of Vn is equals to the composition of Ln. Let's carry this forward to show you how this continues. The 2 streams that are leaving stage 1, which is V1 and L1, will have the compositions that are connected by a vertical tie line as indicated here, because the composition of these 2 streams are the same. Okay, so then if you have V1, to find L1, you will follow a vertical tie line if your equilibrium is of the type y equals to x. Then once we have positioned L1, the next step now, you know the passing stream, that the stream that is passing L1 is V2, and those two streams are connected by a line that is connecting L1 to delta. So L2 will lie on the line connecting L1 to delta. Okay, so like we said, once L1 has been located, we know that V2 is equals to L1 plus delta. Therefore, V2 must lie on a straight line connecting L1 and delta. So V2 will be on the x-axis, on the n versus x line, which is along the x-axis. So V2 can be positioned by finding where the line connecting L1 to delta crosses the x-axis. Okay. Once V2 has been identified and positioned on the operating diagram, we know that L2 can be located by using a connecting vertical tie line going up here. Since V2 and L2 are both leaving stage 2 and therefore are in equilibrium, so we just follow a vertical tie line until it gets us to the n versus y curve here. Okay, once again, once L2 is positioned and located on the diagram, we know that V3 is equals to L2 plus delta. Therefore, V3 must lie on a straight line connecting L2 and delta. Where this line intersects the x-axis, then you can find V3. And then you continue on like that, knowing that L3 now is connected to V3 by a vertical tie line, and it will lie on the n versus y equilibrium curve here. Once L3 has been positioned, you know that V4 will lie on the line connecting L3 to point delta, and you carry on until the L4 that you end up with is at least equal to your target Ln. So these steps can be carried until Ln conditions are satisfied. As you can see here, we need about 4 stages to achieve the required conditions. So this is basically how you will do stage-wise calculation for a variable underflow multi-stage countercurrent leaching. We will further illustrate this with an example just to show you how it works step by step again. Let us exemplify what we have just covered here by use of an example. We are going to look at an example where we are doing multi-stage countercurrent leaching, where a continuous countercurrent multi-stage system is used to leach oil from meal with a benzene solvent. The process is to treat 2000 kg per hour of inert solid meal, which is the solid B, containing 800 kg per hour of oil, which is the solute A, and it also contains 50 kg per hour of benzene, which is the solvent C. The inlet flow rate per hour of fresh solvent mixture contains 1310 kg per hour of benzene and 20 kg per hour of oil. The leached solids are to contain 120 kg per hour of oil. The data of N versus Y is tabulated in this table here. We are required to calculate the amounts and concentrations of streams leaving the process and the number of stages required. We need to show all step-by-step calculation. Just a quick point to ponder on before we continue with solving the example. The leached solids are to contain 120 kg of solute oil. Remember, this solute oil is contained in the solution that is entrained in the slurry. It is in the phase L. We can use a generic block flow diagram to represent the flow rates and composition of all streams. This flowgram that we've been using all along. The mass components of the slurry feed can be basically determined from the given information. We need to determine LO, YO, NO, and B. From the information given, we can tell that A, which is the solute, is 800 kg per hour. The solvent that is entrained in the slurry is 50 kg per hour of solvent C, and we know that the solids B is 2000 kg per hour. The mass of solution, or the flow rate of solution, can be calculated by combining the solute and the solvent, which is A plus C, to get the total entrained solution in the feed slurry, which is now 850 kilogram per hour. The composition of solute in the solution entrained in the slurry can be calculated just by dividing the mass flow rate of solute by the mass flow rate of the solution that is entrained, which we get it to be 0.94. Then the holdup of solids by the solution entrained in the slurry can be calculated by using the mass of solids, which is given as 2000 kilogram per hour, divided by the mass of solution, which is given by the solvent C plus solute A, which we can calculate to be 2.35. This gives us the coordinates for LO, which basically are YO and NO, which we can now position on our operating diagram. The next step, we need to calculate the mass of components and compositions for the solvent feed stream, which is the Vn+1 stream, this stream here, this stream here. We need to find the coordinates for that, which means that we need to find xn+1 and nn+1. We know that the solute in the fresh solvent feed is 20 kilogram per hour. There's no solids in the solvent feed, and the solvent in the fresh solvent feed is 1310 kilogram per hour. So we can calculate the total mass of solution, or the flow rate of solution, to be 1330 kilogram per hour by combining A and C in the Vn+1 stream. The composition of solute A in this stream can be calculated by dividing the mass of solute in the stream with the mass of solution, which is the mass of A divided by the mass of A plus C, which we get to be 0.015. The holdup of solids in the solvent feed stream is always 0, since there are no solids in the solvent feed stream. The coordinates for Vn+1 now can be which are xn+1 and nn+1 are fully determined, which means that we can place this point on our operating diagram. Next, we can use the overall total solution balance, solute A and solvent C, to around the mass balance boundary to find the mixing point M, which we know it will be the mixture of the feed solutions or the mixture of the outgoing solutions. Since we know the incoming solutions, which is the entrained in the slurry and the solvent fresh feed, we can use those to find point M, which we just have to add the two together to find the total mass flow rate of point M, which is 2180 kilogram per hour. Remember, M is the total mixture flow rate of the two incoming feed streams, LO and Vn+1. The next point is we can do component balance A on this for point to determine the composition of point M. We use the very same equation, but now in the component balance format, where we find the mass flow of component A in the incoming entrained slurry solution, and the mass flow rate of component A in the incoming fresh feed solution, which we know that it will give you the total mass flow rate multiplied by the fraction of component A in the M flow rate. You can rearrange that equation, and since the only unknown there, it will be the composition or the mass fraction of solute A in the M stream. You can solve for that and find it to be 0.38. The total overall solid balance around the system boundary can be used now to position point Nm, which is the solid fraction or the solid ratio in the mixture flow rate M. We know that the total flow rate of solids B is given as 2000 kilogram per hour, and we know the mass of solution, the mass flow rate of solution in the M mixture M, so we can use that to find Nm, which we find to be 0.92. The coordinates of M, which are xm and nm, are now fully determined, and then we can position point M on the operating diagram. Next, we need to determine the position of point Ln, which is the final raffinate stream that is leaving the final stage, by determining its coordinates yn and nn. We know that the mass of solute in that stream is given as 120 kg per hour, and then we know the solids remain constants throughout the underflow, which is 2000 kg per hour. We do not know how much solvent is entrained in that, and therefore we do not know how much solution is entrained in that. This makes it a very difficult or a slightly more complex problem to solve. If we were given the composition of the solution in the Ln phase, it will make it easier, because then once you have that composition Y, you can find N, which you can use to do the calculations forward. But now we are given the actual mass of solute, which means that we will need to know, we will need to do a bit of calculations before we can get to finding the mass of solvent and the mass of solution. We know that point Ln is on the N versus Y curve. We can do some calculations to determine the coordinates of this point. First, the ratio of N versus Y for this point can be demonstrated on the figure here. First, we place an arbitrary point Ln to aid our demonstration. This is just an arbitrary point Ln. We place it here. You can choose any position. We know that if we have this point placed, we can draw a dotted line from this point to the 0, 0 coordinate here. The slope of this dotted line will be given by nn minus 0, which is the n at this point minus the n at that point, divided by the yn minus 0, which is the yn at this point, minus the yn at this point, which is 0, which we get it to be nn over yn, because the zeros falls off. We know that nn is equals to b over ln, and then yn is equals to a over ln. If we take nn and divided by yn, we can cancel the ln, and we end up with it just being b over a, and we know what a is and we know what b is. Then we can calculate that given slope of the dotted line as 16.67. Then, since we know this equation is passing through the origin, it does not, the y-intercept is 0. So the equation of this dotted line now can be given as n is equals to mx, or in the n is equals to slope multiplied by y. If we draw a line from 0, 0 with a slope 16.667, now we know the line we want to draw. It will intersect the point n versus y curve at point Ln, because it has that slope of the point that's pointing in the direction of Ln. In order to plot the dotted line, we need to find the second point. So we can just select any other point on the diagram. So we select for a point for y equals to 0.15. Just select any value within the scale of the diagram. Once you have selected the point for the value of y, you can use our equation to solve for n, or at that point. So in this situation, we find the n at the y equals 2.15 to be 2.5. Then we have the 2 points, then we can connect them to find our line. At this line intersects, at the point where this line intersects with our equilibrium line, there lies our point Ln. So then we can read the coordinates from that, which we find them to be 0.118 and 1.95. It's a little bit of a back and forth calculation. This is made difficult by the fact that we are given the actual mass flow of the solute in the underflow stream. Had we been given the concentration, it would have made the calculations much easier, because with the concentration or the mass fraction y, you can just now look at the equilibrium data and find what the value of n is, which will basically get you to this point where you have yn and nn. Now that we have fully defined Ln, we can find whatever information we need to find. we know that we know that yn is a over ln, which can give us to find the mass flow rate of ln, because we know everything. We know a, we know yn, then we can find the mass flow rate of ln, which is the underflow stream that is leaving the extractor. We find it to be 1016 kilogram per hour. We know that ln is equals to the solute in the ln phase plus the solvent in the ln phase. So then we can find the solvent in the ln phase by just rearranging that equation, and we find the solvent in the ln phase to be 896 kilogram per hour. Next, we can do the total mass balance around stage 1. We know that stage 1 has ln coming in and v1 coming in to form m, which is the combine of the incoming stream. Then we can find v1 to be m minus ln, and we have the value of m, and then we also have the value of ln. Then we can find v1 to be 1164 kilogram per hour, and then the component balance on the v to find the x1, which is the mass composition in the v stream. We can do the component balance, and then the only unknown in that would be xn. Then we can solve for xn using that equation, which we find to be 0.62. We know that the point v1 is on the n is equals to 0 versus x line, which is along the x-axis. The coordinates for this point are 0.62 and 0, 0. So then we can position all the points that we've been calculating the coordinates for. We can position LO, we can position LN, we can position M, we can position Vn plus 1, and then we can position V1 in the diagram as shown. Now we have a good starting point to continue with our calculation. The next point that we know we need to do is to find the coordinates of the delta point, which we know it will be the extension of a line that's going through this line, where it intersects the line that goes through these two lines. Okay, let's continue. Okay, as indicated, the coordinates of the operating point delta can be found by finding the intersection point of the extended lines LO V1 delta, LN Vn plus 1 delta, or by solving the equations that we derived earlier in our theory section. You can use those equations because everything in that is known. You can solve for x delta, and then you can calculate n delta to position that point at the given coordinates. Once you have found those coordinates, you can position that point, and then from there everything becomes easy. You can just start doing your stepping off. You know that you draw the first line L0 V1 delta, where it intersects the x-axis. It is your V1 point. Your V1 point is in equilibrium and lies on the same tie line with L1. So where the tie line just crosses the equilibrium line, you can find your L1, and you know your L1 lies in the same line with on the line with L1 V2 and delta. Where this line intersects the x-axis, you find your point V2, and then finding your L2 is following the tie line to find L2. Once you have L2, you can find V3 by following this line. Once you find V3, you can find L3. Once you find L3, you can continue again to find V4. Once you find V4, you can find L4. Then you continue to find V5. Once you have found V5, you can find L5. As you can see, now we have met the conditions that we were targeting for. We have satisfied the LN conditions, so which means that we will need this many stages, 5 stages, to get to achieve the leaching recovery that we were looking for. So this basically concludes our example on multi-stage countercurrent leaching using variable underflow. So let us now look at the next step, where we are going to look at the constant underflow. The constant underflow, the flow rate of L does not change from stage to stage. This will mean that on the plot of n versus y, it becomes a straight line, because if L does not change and B does not change, then N becomes constant, because remember, N is the ratio of B over L. So if L does not change and B does not change, which is the solids in the underflow, then obviously N will become constant. So for this situation, the operating line is given by equation 7, is a straight line when plotted along the y versus x, given by this equation. The equilibrium line can also be plotted on the diagram, and in many cases it will also be a straight line. If you're looking at the y versus x diagram, we are not using the y versus x diagram for our calculations in Leaching this time, but if you are using the y versus x line, you will have the two straight lines. You'll have the equilibrium line, which is a straight line, and then also your operating line will be a straight line. When performing calculations for constant underflow leaching, careful attention must be given to the first stage, where LO is not always equals to LN, since LO usually contains very little or no solvent. So you would find that in that diagram, in the y-x plane, the point LO is off the straight line of your operating line. So it's the only point that is off the straight line. We are not going to be using that the y-x calculation, because we are always using the n versus xy diagram. Okay, a separate material and equilibrium balance calculations will have to be done for stage 1, as we said that stage 1, because of the fact that LO is not equals to all the other L's, because of LO usually has very little solvent in it. We'll have to do a separate material and equilibrium balance for stage 1 in order to obtain L1 and V2. Once this is done, a straight operating line can be used with Mercatial method to step off and determine the number of stages. That is in the y-x plot. Here, since we know that it always holds, the only thing that will be different from what we have done in the variable underflow is that this line now is a straight line. So you will carry on with the calculations similar to as we have done in the variable underflow. Since the constant underflow method requires almost as many calculations or stages as the general case of variable underflow, the general procedure can be used for constant underflow by simply using a horizontal line n versus y, and then stopping off the stages with the operating delta point, as we have just stated right now, that the only difference now it will be that your n versus y line is a horizontal line fixed at n is equals to a constant. So there's not much difference as for calculating the constant underflow. It is similar to the variable underflow, only that your n versus y line is now horizontal. That's why we started with a more difficult one, which is the variable underflow, because now you have a curved n versus y. It becomes a little bit difficult. So here, as you can see, the calculation and the stepping off is exactly the same, so there's no much difference. This will conclude our lecture for this lesson of leaching.